Hi, my name is Manish Gupta, and in this video, I'm going to talk about CALM, which is about how you can use one LLM to augment to the capabilities of another LLM and come up with some sort of compositional capabilities. Okay, so let me first talk about how does CALM work, and then we'll see how does it perform on various tasks. Okay, so CALM actually stands for Composition to Augment Language Models. So the idea is that you have two language models. Let's call them as MA and MB, right? So MA is a particular. So those are two different language models, and in general, MA is a language model which knows a particular specific skill. It is also called as the augmenting model, while there is another model MB, which basically is more like a generic model. It's also called as the anchor large language model. Okay. So for example, a typical in their particular case, in fact, MB is generally PaLM2 extra small or PaLM2 small model. So notice that these models, of course, they are extra small and small, but they're still larger than MA, which is typically PaLM2 XXS model. So this model is small. This model is larger relatively. Okay. So also MA is specifically trained on domain-specific data. Okay, so for example, here three tasks are shown in this picture. So task one, task two, and task three. And let me talk about one by one. So in all of them, basically the same MB is used, while all of them actually contain a different MA, the augmenting large language model. Okay. So basically, in the first case, essentially, MA has been trained on some key value mapping. So MA sort of has been trained to say that X1 is 10, X2 is 2, and so on. So MA sort of rote learns in some ways that the assignments of a particular value to a variable X1, X2, X3, X2, and X4, and so on. Okay. So, and then, MB is a generic math-based model, so it knows how to do typical numeric arithmetic. But if it is told to basically compute what is the value of x1 plus x8 into xn, this model by itself, MB cannot do anything because it does not understand what does x1 mean, x8 mean, and so on, right? So the idea is that if you want to solve this sort of a task, which is a composition of what MA knows and what MB knows, so MA does not know how to do numeric arithmetic because it only knows how to do key value mappings. MB does not know the key value mappings; it only knows how to do numeric arithmetic, right? So while this task is a composition task because it really needs to be done by as numeric arithmetic, but over variables, right? So you need some sort of composition of the abilities of MA and MB, right? And the way this is being done in CALM model, in CALM framework, is basically by bringing in this cross-attention architecture. So you take a few layers from MA. So let's say you take like every fourth layer in their experiments, they take every fourth layer from MA and every fourth layer from MB, or every few layers basically, right? And in these aligned layers, what you do is essentially use the keys and the values coming from MA and the query coming from MB, and come up with these cross attention outputs, which are essentially added via residual connection to the MB model, right? So of course, to be able to do this kind of cross attention, you need to first map your encodings, the outputs coming from a particular layer in MA to the same projection space as the keys and the values expected by MB, and therefore you have a projection matrix, and then you have these attention weights. So from weight perspective, the CALM framework sort of keeps your MA and MB frozen. So MA and MB are kept frozen. So therefore, from a new learnable weight perspective, it's just that the projection matrix is there, and then there are also these cross-attention weights that need to be learned. Okay. So in short, CALM basically involves efficient composition of two large language models to enable newer capabilities, compositional or a combination skill kind of capability. It basically involves only two small learnable, weight matrices, projection parameters and cross-attention parameters. Both the LLMs, MA and MB, participating in the composition are sort of frozen, right? So in this particular example on the left side, which I talked extensively about, was about key value mapping. Now you could actually come up with other two examples. So in this example, MB is again the standard vanilla PaLM XS or PaLM small model in both cases, right? But MA is basically trained specifically on low resource languages. And what this enables is to basically be able to do translation from any low resource language to English, which MB by itself is not very capable of. Okay, as we will see in the experimental results in the next few slides. Similarly, in the third case, MB is a generic model, generic generative PaLM extra smaller PaLM small model, pre-trained model. It does not really know how to generate code as that well, and therefore you augment it using MA, which is specifically pre-trained on GitHub kind of data, so that it is a code, it knows how to generate code, and then the combination of the two can be used to solve various interesting code to text, text to code kind of, or code completion kind of problems. Okay. So that's that. Now, so again, to repeat, the PaLM architecture basically tries to compose two large language models so that they can actually together achieve a new skill that either of the two models is not good at doing, right? And while doing so, it basically keeps the two models frozen, but then learns those parameters, projection parameters, and cross-attention parameters. Okay. Now let me talk about how does CALM perform. So for the key value arithmetic, let's basically see how they designed the experiment nicely. So they took, English. So for the first step is to basically build the key value pairs that you could actually use to train the MA model. So they basically got like English strings of length 2 to 6 characters from vocabulary of PaLM to XXS as keys. And then they basically put values in the range of 1 to 25K, right? So basically this data set size is also 25K, so 25,000 examples in that sense. Okay. And then what they did was to basically create a very large collection of arithmetic expressions involving 3 to 6 keys with operations of plus minus multiplication between them. And the keys are randomly sampled from this 25K set, right? And then they created three different interesting subsets. So DKV subs, basically, which essentially tries to map the key value pair expression to a numeric expression. It doesn't solve it. It just basically learns mappings. Okay. And this is where basically, this is the data set which is used to train MA. Remember, I told you MA basically knows how to do key value mapping. And the way it is trained to do key value mapping is by taking these arithmetic expressions with variable with the keys in as input, and then trying to map it to an equivalent expression with the values in the output. Okay. So key value arithmetic basically is a data set which actually is the target task data set, which basically takes those keys, arithmetic expression, and comes up with the value. And then, of course, this is the standard numeric arithmetic data set, which MB model is really good at solving anyway. Okay. So what you do is to essentially train your MA model using substitution data set, and and you train the overall CALM model using a small part of the DKV math data set. So this one, DKV math data set, a small part of the target task, right? And then you compute the accuracies. So what we observe is that MA model is really good at substitution task because, well, it has been trained to do so. So of course it is really good at substitution task. Makes sense, right? Now MB model is in general a good model. It's a large model, so it basically does really well on standard arithmetic, numeric arithmetic, which also makes sense. Now, if you take like the KV math data set, so remember the KV, the composition data was very small. So it's not like, while composing, you basically saw all the key value pairs and their arithmetic expressions and so on, right? So in fact, you take the DKV part, which has already been used, and then the evaluation is done on the remaining part, the expressions which are not a part of the composition training. Right? And what you observe is that MA and MB both are bad. MA is bad on this data set because MA is a model which does not know how to do numeric arithmetic. It basically only knows how to do substitutions of keys with values, right? MB is bad because it does not really understand what K1 means, what K2 means, what K3 means. It just knows standard arithmetic in that sense. It doesn't understand the keys, the values of those keys, right? But the CALM model really gives you really good performance, basically showing that, yes, this kind of a framework works where you can augment two LLMs to be able to get compositional abilities. Now, in the low resource language inclusivity task, what you do is, again, train your MA model using low resource language data, which is obtained from the next 1,000 language corpora, which is the corpora for 1,000 languages. Okay. It basically contains both monolingual sentences and translation pairs. Okay. Now, composition training, compositional data basically is 5% of this next 1,000 language data. So, of course, typically you have to basically do the CALM training using target composition domain dataset. For example, in this particular, in the key value arithmetic case, it was the DKV math dataset. In case of language inclusivity task, it's basically low resource language dataset, and in case of this code generation task, it's going to be GitHub code dataset. Okay. So that's what, so basically in the low resource language inclusivity task, you basically use this next 1,000 language low resource data set to train the MA model. And what you observe from this table is that basically the experiment with Flores 200, which is a data set of 200 languages, and results of 10 languages are shown here with an average over 200 at the end. And what you observe is that the CALM model is actually better than both MA and MB models, on average as well. And basically, in fact, it is better on 175 out of 192 languages on which it is sort of evaluated. What is further very interesting is that if you took the MB model, which is a large-sized model in that sense, well, it's PaLM2-S or PaLM2-S, right? PaLM2-S basically, but still it is much larger than PaLM2-XXS, right? So you take the MB model and you do further pre-training using the same data which you basically used for CALM training. Then what you observe is that you can actually get better results. However, the overall compute power required to train this model is much higher, right? So essentially, you can actually obtain reasonably accurate results using the CALM training with a way lesser amount of compute. The third task for evaluation is code understanding and generation, where they basically try to evaluate on 3 different tasks, code completion, text to code, and code to text. So they train the MA model on open source data from GitHub, open source code from GitHub. They also, do similar kind of an experiment here where they train the MB model, further pre-train it with the same, open source code from GitHub. And what you observe is that the CALM model is better for all the 3 tasks, code completion, text to code, and code to text compared to MA or MB, right? But also interestingly, it is better compared to MB code. The MB model further pre-trained on the same code, source code data from GitHub. Yeah. Basically just shows that if you take the MB model, it unnecessarily causes catastrophic forgetting of the text generation task by the MB model itself. Okay, but CALM, because it keeps the MA and MB frozen, basically it leads to no catastrophic forgetting of the pre-training part, right? So in this case, of course, the composition data was 7% of the same GitHub code data, which was used to, evaluate these models. Okay, so of course, the remaining 93% is used to evaluate these models in that senses. So broadly, what you observe is that compared to MA and MB, the CALM model actually achieves plus 6.1 and plus 3.6% absolute pass at 1 gains. So pass at 1 is a very interesting metric for code generation. And it's evaluated over 2 benchmark datasets, human eval and MBPP, which are code evaluation benchmarks, code generation evaluation benchmarks. Pass at 1 basically means that was the model able to generate code which could pass the which is accurate, right? So which is the first code piece that is generated by the model, is it accurate or not? Okay. So in summary, in this video, I talked about CALM, which stands for Composition to Augment Large Language Models. It composes 2 large language models to enable newer capabilities. It involves training of projection layer and the cross attention across various layers between MA and MB, the two models. Both LLMs are kept frozen, and it showed good results over key value arithmetic, language in low resource language inclusivity and code understanding and code generation, right? So, I mean, although the PaLM model is interesting, but I mean, as a critique, I sort of find that you see, I mean, to be able to achieve better capabilities, you need to sort of, at inference time, you'll need to maintain both MA and MB. Now, which basically is bad because, in RAM, you have to basically manage two different models now. Now, it's not just about RAM, but it's also about maintaining. If you have to train, you have to train both the models again later. I mean, if you want to basically keep them updated against model drift and so on, right? Similarly, the compute power required to actually do this is higher because now you have to do inference over two models in that senses. So, I mean, well, I mean, CAM is okay, but you see, I mean, if I have to deploy this to run over millions of users every day, I would rather just go ahead and do more careful pre-training and fine-tuning of the MB model rather than maintain two different models. Okay, but anyway, that's how CAM works, and it could be useful for multiple use cases otherwise. Hope you liked the video. Thank you for watching. Connect with me on my LinkedIn or look at my search on my homepage. Thank you.